So the numbers that are there are the location of the source. So in particular, I'm going to talk about this Pulsar Wind Nebula, which is the SG1825-137, which, we had the introduction before about the balloons, and I'm going to talk about here the results obtained with the Fermi-LAT, which is a satellite. And in particular, we'll talk about this nebula, which is particular because it is a candidate TV halo and Pevatron candidate. So here are listed also my collaborators, and I'm Giacomo Principe, a postdoc from the University of Trieste. So about the content of the presentation, I will give a short introduction about Fermi-LAT and the gamma ray sources observed. Then I will talk about the Pulsar Wind Nebulae and the special case of G1825. And then I will focus on our project, namely, so the description of the analysis and our results, the modeling of the Pulsar Nebula in order to characterize the physical parameters in this source, in order to understand also the particle acceleration mechanisms that are going on in this environment, and some future perspective. So about Fermi-LAT, the large area telescope, namely also LAT, is the main instrument on board the Fermi satellite, and it observes in the entire sky in 3 hours, and it detects photons using the pair production effect, as you can see here, between 20 MeV and more than 300 GeV. And with together with the LAT, there is also the gamma ray burst monitor, which instead is searching, so looking at the entire sky, so unocculted by the Earth, the bursts which are come in the energy range between 8 keV and something like a few MeV. So this is the sky, as you can see here, the gamma ray map, so the CANS map of the sky seen by Fermi. So at energy is greater than 1 GeV, the sky is pretty different from the sky seen by the optical sky. And we can see that we have a bright gamma ray emission from the galactic plane, so this diffuse emission. And then we have several sources that you can see here as a point like outside the galactic plane. But if we analyze and we resolve the background from this map, we could arrive to a number of like 5,000 sources, as in the latest Fermi-LAT catalog. And most of them are AGN, so here labeled with these blue crosses, while in red we can see the galactic sources. As you can see here, the galactic sources are just few, and in particular we have only 17 Pulsar Wind Nebulae in our catalog. So, but what is the Pulsar Wind Nebula? So this is a nebula which is formed when a star died, and then we have formation of a neutron star and then a pulsar. So the nebula is come from the acceleration of electrons from the pulsar that due to the really strong magnetic field and the offset between the rotational and the magnetic axis, we could have a strong also electric field, and the electrons are able to escape, and then they are accelerating the environment from the polar cap. When they started to interact with the interstellar medium, so the environment around the nebula, they start also to have this shock, and they could again accelerate inside those shocks. So about those Pulsar Wind Nebula, they are very interesting for 2 reasons. The first one is that they are good targets for constraining the particle acceleration mechanism, in particular because those are like natural laboratories for particle acceleration. And the second one is that they are considered as Pevatron candidates. What does it mean, Pevatron? So we can see from also the plot here that we observe in the Earth cosmic rays up to very high energies. And we believe that till the CNI, so till about 1 PV, the origin of those cosmic rays are from our galaxy. Instead, above 1 PV, we think that there are no sources in our galaxy able to accelerate particles up to this energy. But we don't know which is the origin and source of such particles, because we cannot trace back, because due to the magnetic field that we have in our galaxy, so we cannot trace back from the direction of the particle. We could instead trace back using the photons. And Pulsar Wind Nebula are possible Pevatron candidates, because due to this really strong magnetic field, are able to accelerate particles till up very high energy. In particular, the case of SG1825-137, it is a pulsar nebula which has been first detected in the survey of the galactic plane done by the S collaboration. So this the S is a Cherenkov telescope collaboration, and so at TV energies, and then performing more than 67 hours of observation, they obtain a even more resolved map from which they could see this extension in TV energies. And they associate this extension to the nebula, which is connected to the Pulsar G1826, which has a characteristic age of 21 kiloyears and a distance of 4 kiloparsec. At other wavelengths, so X-rays, this source is also observed by XMM Newton and also Suzaku, and it presents a bit smaller extension, but again around 0.1 degrees. So it is also extended, and the emission does not come only from the pulsar, but also from the environment. This means that there are electrons that are accelerated also in the surrounding environment. And this source has been also seen recently at very, very high energies. So I mean, the highest energies observed now with the light, so above 100 TeV by the HAWK, so which is the high altitude water Cherenkov telescope, and the SJ1825 is one of the 3 sources observed above 100 TeV. And here you can see the spectra with this gray band here. And in particular, so this is the brightest source above 100 TeV, making this source a really promising Pevatron candidate. But our work was also triggered by a recent work by the Hess collaboration, where they found, so they studied again this source, and they found that this source has a size larger than 100 parsec, which is the largest pulsar we nebula currently know by this size. And they also found a really strong energy-dependent morphology. What you can see here are the excess maps, so the extension of the source, moving from energies below 1 TeV to above 32 TeV. And what you can see here is that the extension starts to decrease and goes toward the position of the pulsar from where the electrons are accelerated. Similar here in the plot on the right, you can see that we have the radial extent versus energy, and you can see that it starts to decrease. And here 2 different particle acceleration mechanisms are compared, diffusion or advection. So if we have a diffusion, so a more isotropic acceleration of the particle, or instead an isotropic, a preferred direction for the particle acceleration, which driven toward some preferred direction, making it possible also to expand to very huge, let's say very big sites, so reaching 100 parsec in this case. So about our analysis, we performed the analysis using almost 12 years of Fermilab data between 1 GeV and 1 TeV. So this is also about the first general analysis of the source, but in particular we performed an energy resolved morphological study in the GeV domain, which was not was performed by Hess above 1 TeV. We expanded the energy range going down to 1 GeV. And here you can see the parameters that we use in our analysis. So if you are interested, the Fermilab provides all the data are public, as well also all the scripts. So it is possible to repeat this analysis using these parameters. So about the results, here you can find the count map of this source. So here in red is labeled the extension that we found. And in particular, we found an extension of almost 150 parsec, which is larger than a previous observation done at such energies, like in a paper published by Grondin et al. In 2011 and another one in 2017. This thanks to the improved analysis and also to the more statistics collected. But coming also to the spectra, so we compare the spectra that we found here with the red points with the Hess spectra, in order also to detect which is the energy break, so the energy at which we start to think that the electron starts to cool. So the electrons, we expect that they are accelerated up to such energies, and then the cooling mechanism start to dominate more than the acceleration. And then we, as I said, we perform the first energy-dependent extension in the GV domain. And as you can see, as we also observe a higher energy in the S, we see that the extension first start to increase, but then starting from 10 GV, the extension start to decrease and moves toward the position of the pulsar that is labeled here. It is represented by this gray point. And here are compared the giant contours are the S, it is the S morphology. So the results that we found is compatible in the same energy range, which is observed both from Fermi-LAT and from the Cherenkov telescope. We obtain compatible results. This helps us also to close the gap, so going down to 1 GV. And similarly, we perform the study of the morphology also using a radial profile method, because the other method was a 2D Gaussian, which is a more symmetrical. But we think if we believe that is the pulsar that accelerates the particles, then we could consider to count the extension starting from the pulsar position, and then we define the extension till the value at which the flux drops to a factor 1 over E with respect to the maximum. And combining both the results, so the results using asymmetric shapes, so 2D Gaussian, with revised by counting by the shift between the center of the 2D Gaussian and the pulsar position, we can then compare the results with the S results, so above 1 TeV, and we can see that the extensions start to decrease, going up to higher energies where the electron cooling starts really to dominate. We then try to model the source using two different modeling programs, like the NAIMA SD modeling, which is a single zone model, and then also a Gamera model, which is using multizone. But in particular here, we use an emission, so leptonic emission from, so with the inverse Compton from the electrons. And we use also the X-ray observation in order to constrain the magnetic field. And what we find is that the energies, so the total energies that we found of the electrons in this nebula is around 10 to the 39 ergs, so 2.33, 10 to the 39 ergs. Similar results we found also when we consider a multizone modeling, so using different shells which expands, and they expand until they reach the system age, and using burst-like injection for the particles. And you can see here the different shells that if we sum together, we could fit our data. And in particular, we can also represent why the extensions start to drop, because we can model and describe that the electron cooling starts to dominate above around 1 TeV, or let's say a bit before, where the electrons start to cool, and then the extension that we observe start to reduce, because only the electrons which are closer to the pulsar can reach, so only those electrons are observed, and not so many can reach farther distances. So about the pulsar nebula evolution, what we observe is that the centroid, so the center of the 2D Gaussian of the extension, moves, if we move from lower toward higher energies. So, and it moves in the same direction of the pulsar proper motion. But what we can see is that the shift, so if this is the shift, so in blue is so black is the current position of the pulsar. If we believe that the pulsar has 21 kiloyears as the characteristic estimated age, the blue point is the obtained one, while what we see is that the shift is much larger than what we expect from the pulsar proper motion. This means that the particles are probably accelerating in a preferred direction, and that's why we have such a huge extension and also this shift for the centroid. So the electrons at lower energy have moved much faster than the other electrons, which are probably generated in the latest period, so that are closer to the pulsar. Then coming to what I said at the beginning, so this nebula, it was also classified as a possible TV halo because as by definition, the TV halo, they say that are the halo when the electrons start to escape from the supernova remnant and they start to directly interact with the interstellar medium. And when the electrons are completely outside, then we can call it halo. In order to understand which is and define which is our halo or not, we can compare with the energy density of the electron. And if the electron energy density is much lower than the electron energy density of the interstellar matter, this means that the electrons are confined by the interstellar medium and they are not more surrounded by the supernova remnant. And then by a result, so a recent result by Giacomo et al., they found that this source can be classified in a transition between a pulsar nebula and the TV halo because it has an energy density of the electron which is exactly 0.1, so similar to the interstellar medium. And we found in our work compatible results confirming that this source is a composite pulsar nebula TV halo case. So for future perspective, so the future, after also Fermi and the other Cherenkov telescope, CTA will be the next biggest observatory in the gamma rays, which will cover as a single instrument the energy range starting from a few decades of GV up to hundreds TV. And in a unique instrument, it can cover what at the moment Fermi-Lat, the Cherenkov telescope, namely such MAGIC or HESS or Veritas, and then also the OAK, so the water Cherenkov telescope are covering. So with the 3 different instruments, the CTA will be able, with a unique instrument, with a telescope with different sizes, to observe what we see at the moment with the 3 instruments. So concluding, so these results, which have been also recently published in a paper in A&A, here you can find the coordinates, is present the first energy-dependent morphology study done in the GV domain. And in particular here, we characterize this source and we investigate the pulsar nebula TV halo nature. Here also are study some future perspective for CTA. And I would like to thank you for your attention here for questions. So thanks.
Thank you, Giacomo. Excellent work. I have time for one question. If somebody wants to ask something, if not, I won't make a question.
Please.
For me, it's very hard and very interesting the way that you process the data. HESS G1825 is colliding with a molecular cloud.
Yeah, this is the reason why we see this this not symmetric shape, because as you can see also here, so from the pulsar we have molecular clouds here in the northern part, and this make that almost all the electrons are accelerated toward the opposite direction, and that's why we have this preferred direction.
Okay, the main problem is the collision or the presence of magnetic field.
So both, because first is the presence, so the magnetic field, and in particular the electric field, and makes gives a preferred direction for the electron to accelerate. But then this when they start to accelerate and they start to interact with the medium, so starting from the pulsar, when they start to interact with the medium, then they are stopped because there is this dense region for this molecular cloud, which makes the electrons to stop and then to push toward the opposite direction. The other electrons, when they come, they are pushed on the opposite direction.
Okay, thank you.